Welcome, my young Padawans, to Lesson 2.1, Transformations of Quadratic Functions. Before we get started with the actual lesson, I want to talk to you about the original parent function y equals x squared. This, of course, is that same parent function that we learned about back in the beginning of Chapter 1 for the quadratic equation. And I want to talk to you about the table of values that we use to create this graph. So I'm going to use a couple other values that I don't normally use. I'm going to use -3. I'm going to go all the way from -3 all the way up to +3 and give you these values. Now again, this table of values is very familiar. You saw it before, and if you don't know where I got the -3 squared, -3 times -3 is 9. So we end up with those values there. The table of values in developing the table of values is not the important part for this. Rather, it's the pattern that is created. Notice here, 0, 0. 0, 0 is the only pair of y values that doesn't have a buddy, right? You look at -2 and +2, they both go to 4. You look at -1 and +1, they both go to +1. You look at -3 and +3, and look here, the y values are the same at 9. And if you notice, these values are the same, right? They have the same value, the same y value when they're across from each other. This is a really important property that quadratic equations have, and I wanted to point that out to you here. There's a little bit more to it than that. I want you to also notice how these numbers go up. Like if I'm going from 0 and in either direction, you'll see that I'm going up 1. And then when I go from 1 to 4, the y value, I go up 3. And then when I go from 4 to 9, you'll see that I'm going up 5. And you should see this pattern in both directions. It's kind of a really nice shortcut for you to notice. You'll see here, see I'm going up 1 unit on the graph. And then I'm going up 3 units on the graph. And then I'm going up 5 units on the graph. And guess how many units I'd go up to get to the next point? 1, 3, 5, you got it. 7 follows consecutive odd integers, and that's kind of a really nice shortcut that you can use when you're graphing some of these quadratic equations, especially after we find this guy right here, right? That's a really important point. We'll get to that here on the next couple slides. So I want to remind you of those transformation rules that we already learned with absolute value graphs. Not any different with quadratic equations, except we're using this curve instead of that v or the linear equation. So everything's going to be exactly the same as what we saw before. So let's focus first on that horizontal transformation, right? In that horizontal transformation, our graph can move to the right. Let's move it to the right 4 units. And of course, this would give me the equation y equals f of x minus 4, right? Because that h value would be equal to 4. And that would give me my quadratic equation of x minus 4 squared. And in order to do that, all we do is we take each one of those points and we move them to the right 4 units. So here we go to the right 4 units, and we can still kind of use that pattern that we saw, and we can move everything over to the right 4 units. Whoops, that point should be here instead. We can come up with a graph that looks like that. Or, of course, we could also come up with one that would move it to the left. Let's move it to the left 2 units. And of course, in this instance, remember, left 2 units means that h is equal to -2, not +2. So my equation would be y equals f of x plus 2. Which would give me the quadratic equation x plus 2 squared. So I'd move all my points over to the right 2 units. So let's see here, that one would move over to the right 2 units, and that would move to the right 2 units, and then that would move to the right 2 units, and we'd end up with our curve being over here like this green curve. Okay, and that's the horizontal transformation. Next, let's remind you of the vertical transformation. So this moves the graph up and down. So, for example, we can take this graph and we can move it up 4 units. And of course, the equation, that would make my k value equal to +4. So my equation would be x squared plus 4. And we take each one of those points and we move them up 4 units, right? So that guy would be up 4 units. He's up 4 units. This point's up 4 units. This point right here, that would go up 4 units. All of my points would shift up 4 units, so my u would be up here like this. Or I could move it down. I could move it down, say, 3 units. And of course, in this instance, my k value is -3, so my equation would be x squared minus 3. Same idea, but I'm moving all of my points down 3 units. So that would be down, and that point would be down, and this point would be down. I'd have my point up here that would be down 3 units. 1, 2, 3. And I'd be able to create my u that would look a little something like this. So vertical and horizontal transformations, just like we learned with absolute value graphs. So let's go through an example problem. So I have my equation here. I have my equation, x plus 4, that quantity squared minus 1. So instead of me giving you a list of transformations, I'm going to give you this equation. And it's kind of up to you to figure out what those transformations are that happened. So I'll look here first. I'll look on the inside of those parentheses, and I'll see an x plus 4. Now, I'm not used to seeing that. It should be x minus, and then that'll tell me the h value. So I got to remember that it's x minus -4. That's what will give me the plus 4. And then I have this minus 1 that's at the end there. So that should give me a really good indicator that I'm looking here that that's a -4. So that means I'm going left 4 units. And then I should see this minus 1 right here that tells me I'm going down 1 unit. Now, if I look at my table of values that I start with, right, that normal table of values that I start with for every quadratic equation, I got a couple different ways I can think about this. The first is to actually perform the transformations by using a table of values. So I can say, okay, left 4. What does that mean? That means I'm going to subtract 4 from my x values. Because if I do that, right, if I'm moving it to the left 4 units, what happens? All of the x values are becoming smaller and smaller. So let's see here. So let's see that. That means that my y values are not going to change at all. So I can fill those in first. Okay, but my x values are all going to be reduced by 4. So let's hear. -2 minus 4 is -6. -1 minus 4 is -5. 0 minus 4 is -4. 1 minus 4 is -3. 2 minus 4 is -2. So I have my new table of values that I can use that would show my graph just shifted to the left 4 units. The next thing I'm going to do is I'm going to move it down 1 unit. So what does that mean? That means I'm going to subtract, again, because I'm moving down. I'm going to subtract a 1 from my y values. Okay, so let's hear, what does that mean for this new table of values that I have? Well, my x values are going to remain the same as they were in the previous step because I'm moving my y values and only my y values. And I'm going to subtract 1 from each one of my y values. So 4 minus 1 is 3. 1 minus 1 is 0. 0 minus 1 is -1. And I'll keep going from there. And I'll come up with this table of values. That should give me the new graph that I can just go right out here and plot it. So let's see, I'll do it right in red here. So let's see, I can plot -6, 3. So -6, 3, that's this point right here. -5, 0. -4, -1. -3, 0. And -2, 3, which is that point right there. I can draw my u in there, just like that. And there's what my graph would look like. If you look, you'll see that the vertex right here, that was shifted to the right 4, 1, 2, 3, 4, and then went down 1 unit, cool. And each subsequent point also moved to the left 4 and then down 1. So this guy right here, left 4 and down 1. This point right here, left 4, down 1, to come up with my new equation. I think it's also really important to point out to you where this point right here is, that vertex point. That vertex is at the point -4, -1, as opposed to the point that it started at, which was at 0, 0. Right? So if you see 0, 0 move to the left 4 and down 1, goes to the point -4, 1. If you knew where the vertex was, everything else just kind of really falls into place, especially when you follow that pattern that I had outlined on the first slide. So why don't you take a minute right now and pause the video? You can try this one out, right? Think about where the vertex is, think about where the transformations are going to occur, and give this one a try. See if you can figure out which direction I'm moving and what your final graph's going to look like. Go ahead, pause the video right now, give this one a try. So you should have seen that this is going to the right 2 units and down 2 units. So if I didn't know anything else, right, that would tell me that if I would go to the right 2 units and down 2 units, that my vertex is actually right here, right over in that words where I got there at the point 2 comma negative 2. That's where the vertex is. If you come up with that table of values, then you should be able to plot these points that I'm putting on there right now. And your final graph should look like this. Now, if you want to do out that table of values, no big deal. You can totally do that. I'll show you the work for that now. So you should end up with this table of values right here. Let's take a look at 2 other transformations. The first, a reflection over the x-axis. So let's take a look at the reflection over the x-axis. So what does that do? Well, that, of course, would take every point that we have here above the x-axis and put it below the x-axis. So 0, 0 would stay put. But this point right here, 1, 1, that would come down here at 1, negative 1. Right, same thing here. That would reflect down. Look at this point up here at 2, 4. That would reflect down here and go to 2, negative 4. Same thing here. Right, this point right here would come down to go to negative 2, negative 4. And your quadratic would, of course, open down instead of opening up. So that's really just as simple as multiplying the y values by negative 1, as we've seen before. Reflection over the y-axis. Well, what happens here? That means that the point that's here on the right side of the axis, here at the point 1, 1, would go over here to on the left side, that number of units. And that point that's over on the left side, go over here on the other side, to the right. Huh, that's interesting. That's at the same point. What about the point 2, 4? 2, 4 would reflect over the y-axis, come over here to be negative 2, 4. And the point negative 2, 4 would reflect over the y-axis, come over here to the point 2, 4. Well, you end up with the same graph here when you're reflecting over the y-axis. Now, that's only true if you have not shifted to the right or to the left. If you shift to the right or to the left, then, of course, we're not going to end up with the same graph. But, you know, if you haven't shifted left or right, then you end up with the exact same thing, and there's really not anything to do. And, of course, we have horizontal stretching and shrinking and vertical stretching and shrinking. Let's look at horizontal first. Horizontal stretching and shrinking will take these values and we'll stretch them either this way across the axis, right? And that would spread it out. It spreads the graph, okay? So it would look like this. So maybe you end up with a graph that is just really stretched a lot horizontally. Or maybe it's shrunk horizontally, and instead it goes in towards the y-axis more, and you end up with a very narrow graph. And then we have the vertical stretch. The vertical stretch kind of can make the graphs look like the same thing, right? But instead of us moving and moving based upon the x values of the graph, we would move the y values up and down. We're stretching it vertically. So we might pull the graph in this direction, might pull the graph, the 2 ends of the graph. And what happens in that instance, we end up with a very thin and narrow graph. Or we could compress it, or we could like push it down towards, the x-axis, and it kind of would give me a wider graph in that particular instance. Let's take a look at an example problem. So here we have g of x is equal to negative 1/2 x squared. All right, so 2 things. First, notice that negative sign. That negative sign would tell me that there is a reflection over the x-axis. Now, how do I know whether it's the x-axis or the y-axis? Well, the bottom line is there's no parentheses, right? There's no parentheses. We don't have anything going on inside a set of a parentheses. So that's how I know it's a reflection over the x-axis. It's the same reason that I know that this 1/2 right here, this 1/2 is a vertical. It's a vertical stretch or shrink. for our particular problem. In this case, it will be a stretch. So a vertical stretch, because again, it's not on the inside of the parentheses. Now the good news is when it comes to doing the math for this particular function, right, we really only have to do one step with our original table of values that we use. Only really one step. It's kind of like a one-stop shop that we're going to do here with this. And we're going to do both the reflection over the x-axis and the vertical stretch. And in order to do that, what we're going to do is we're going to multiply the y values, the y values, let's spell that correctly, the y values by -1/2. When we multiply the y values by -1/2, it's going to give us with this new table of values that we're going to use to plot our points. So we'll take each one of the numbers, multiply by negative. So 4 times -1/2 is -2. 1 times -1/2, of course, is -1/2. 0 would be 0. Again, we do that multiplying by 1, and then 4 again. So, okay, so let's plot these new points and see what we end up with. So there's 0, 0's here. I got -1, -1/2. That would be the point right there. And then 1, -1/2 would be there. And then I'd have -2, -2. And I'd have 2, -2, which is there. So you see what I end up with is I end up with this wider U than what I'm used to seeing. A wider U. I could do it all in one step. Again, if it was on the inside of the parentheses, we'd do something different, but here we're on the outside of the parentheses. And folks, that's where I'm going to keep it. I'm not going to try to confuse you by doing anything that's going to do any of these other transformations that aren't vertical or over the x-axis. I don't want to try to confuse you with things. So here's a different problem. H of x is equal to 2x squared plus 1. Now notice you will have two transformations that will occur here. So let's identify what they are before we try to do them. So take a minute, see if you can figure out what the two are before we go through the steps to graph this. So go ahead and figure out what the two transformations are. You should be able to tell what they are. Did you say vertical stretch by 2 units and up 1? Because if you did, you would be 100% correct. So just to get the math here for us, we'd start off with that same table of values that we've been using the whole time. Do you notice how I keep coming back to that? And we got to do this in a certain order based upon the order of operations. We want to do that vertical stretch first, so we're going to multiply all those y values by 2, and we'll get this table. And next, we're going to move everything up 1 unit, and we end up with this as our resulting final table right here. If we plot those points, we end up with a graph that looks like this. You'll see that my graph does in fact look narrower and is shifted up 1 unit. This form that we've been using is called Vertex Form, and this is the general form of Vertex Form for a quadratic equation. You'll see that the vertex, when we shift to the right and to the left, and when we move it up and down, h, k, that coordinate pair will become my vertex. And A does some things too for us. Remember that A is going to be that positive and negative that we might have in front. It's going to control two things, just like we did with all of our other quadratic equations, all of our other transformations of equations that we saw. So when A is greater than 0, we know that my quadratic equation is going to open up. It's going to look like a U that goes like this. And when A is less than 0, my quadratic equation is going to open down. So we get like a U that faces downward instead of upward. The other important characteristic that we'll have is you should see that these quadratic equations are kind of cut in half. So they have something that's called the axis of symmetry. Axis of symmetry. And for our particular equation, when it's in vertex form, my axis of symmetry is at x equals h. We'll see more about all this stuff. Algebraically, there's some things that we can find too. We can find a y-intercept. Right? And to find a y-intercept, let me remind you that all you do is you set x equal to 0, and then we simplify the expression. As we're going to here see with these problems. Also want to remind you that the domain of any quadratic equation, all real numbers, and the range, well, that's going to depend. It's going to vary based upon each equation, as we'll see here on the coming slides. So I'm going to show you two different ways that we can approach this problem. We're going to kind of just go through the whole thing here. First of all, we should identify AH and K. Now, what the heck's AH and K? Well, in that previous slide, that's vertex form. So A is going to be the number that's in front of the parentheses, H in the middle, and K would be the number I'm adding on the end. So let's see here. So A is this number right here. That would be 1. There's nothing there. H would be the value that we're subtracting. So I'm subtracting 3, so my H value is 3. And K is this number here that's on the end. So in this problem, 2. All right, so based upon that information, I see here that my A value is greater than 0. So that means that my equation is going to open up. All right, so this guy's going to open up. The y-intercept, okay, I got to do a little work for the y-intercept. So remember, y-intercept is when x is equal to 0. Okay, so I'm going to go up here. Y-intercept, x is equal to 0. So for my equation, y equals, that would be 0 minus 3 squared plus 2. I just made x equal to 0. So that gives me negative 3 squared plus 2, which is 9 plus 2, so 11. So my y-intercept is 0, 11. You want to make sure you write the y-intercept as a coordinate pair, right? So you don't get confused there. The axis of symmetry. From the previous slide, that was just x equals whatever the h value is, and in this particular problem, that's 3. So what does that mean? The axis of symmetry means that here add positive 3, at the x value of 3, that's going to be the imaginary line that's going to kind of divide that parabola in half, right? Every parabola, we can kind of like get that U shape, so my bottom of my U is going to be on that axis of symmetry. Also, based upon the numbers that I came up with, h comma k is my vertex. So h is 3, comma, k is 2. So my vertex is at 3, 2. So I could go ahead and actually plot the point 3, 2 right there. That's going to be my vertex. And knowing that this thing opens up, right, opens up, and my vertex, I can kind of get my U shape, right? There's my U shape. I'm chasing it here with the lightsaber. U shape, okay. So we're going to actually get some other points here, though, because I think it's important to get more points, but that should be the general shape that I see. Before I go any further, I already know my domain. It's from negative infinity to positive infinity. Ooh, that's the fancy way of writing all real numbers. Maybe you remember that from Algebra 1. And the range. Well, let's see here. If I know my U is going to open up, and I know where my vertex is, I know all of my values have to be greater than or equal to that lowest y value, which is 2 in this particular problem. So y greater than or equal to 2. Now, if you can't get the range yet, that's okay. Once you get your table of values, you'll be all right. So we'll start off, if you want to get a better table of values, some new points here, right? We can start off with that table of values that we're used to seeing, that we've used before. And then let's see here, what are my transformations? Well, based upon what I see in my parent function, I should see that I'm going to go to the right 3 units to get to a new table of values. And then I'm going to go up 2 units based upon the transformations that I see to get to my final table of values. So let's see here. Let's fill in those table of values now. So once I do that, I know that I have to add 3 to my x values to move to the right 3 units. And then I have to add 2 to my y values to get them to these coordinate pairs. Once I do that, I plot my points. So I got the point 1, 6. I got the point 2, 3. 3, 2, which I've already plotted. I can use my axis of symmetry to come up with these other 2 coordinate pairs. And I can graph myself a nice quadratic equation. I'd fit that y-intercept of 0, 11 on my graph, but it's like up here and it's not going to quite fit. If I wanted to, I could make my graph go up that way if I wanted to. See, okay. Very good. Let's try another one. Oh, before we do, you can see here clearly that y is greater than or equal to 2. That's these values and up for my range values. Okay, now let's try that other example. Same idea here with the 1/2 x squared plus 2. Let's see if we can identify all the parts. So, try along with me here. Did you get a is equal to 1/2? H is, well, there's no parentheses, so h is 0 and k is 2. So if you're thinking about this in terms of transformations, you should see that vertical stretch or shrink and then moving it up 2 units. So let's see what happens here in this particular problem when we do that. The a value is positive, so it's going to open up. The y-intercept, let's do some work for the y-intercept. We'll make x equal to 0. So let's see here. That is 1/2 0 squared plus 2, which will equal 2. So my y-intercept is 0, 2. The axis of symmetry. The axis of symmetry is going to be at the h value, so x equals h, which is 0 in this particular problem. So that means that the y-axis is actually the axis of symmetry. The vertex, h comma k, so 0, 2. The domain, all real numbers. The range, we'll come back to that. So let's figure out what this graph looks like. I'm going to go ahead and I'm going to do the work for us to come up with this table of values and then walk us through how I did the work. Okay, so I started with my normal table of values. A vertical stretch by a factor of 1/2 means I multiply the y values by 1/2. I come up with these numbers. And then moving up to and adding 2 to the y values. Hey, notice here, -1 goes to 5/2 and 1 goes to 5/2. The number is actually 5/2, but it might be easier for you to think about it as 2.5. But I like improper fractions better. So let's plot my points here. So -2, 4, -1 and 2.5, 0, 2, 1, 2.5, and then 2, 4. So I get a wider quadratic equation that looks like that. The range. Okay, what about the range? It's from here and up. So again, I have y greater than or equal to 2 for the range. If you wrote that in that interval notation, you might write it like this, 2 to infinity. Whichever way you're more comfortable with, I'll accept both. Why don't you try to do this one on your own? Example problem number 3. Y equals -2 times the quantity of x minus 1, that quantity squared, plus 2. Pause the video now. I will incrementally do this in steps, so I'm not going to reveal the entire answer to you at once. Instead, we can stop and start the video a couple different times with this problem. So go ahead, pause the video now, get as far as you can working down in the same order that we've been doing. Okay, pause the video and we'll reveal a couple parts of the answer as we go. The first thing, make sure you have your value for a, h, and k correct. A should be -2, which we can see right here. H is 1 right here, and k would be +2 right here. Next, because a is negative, you should see that your quadratic opens down. Pause the video again and we'll fill in a couple more of these things. The x-intercept is 0, 0. You can find the math up here in the corner. The axis of symmetry is x equals h, which is 1 in this particular problem. The vertex, h comma k, so 1 comma 2. The domain, all real number. So plotting the axis of symmetry, put the axis of symmetry right here at +1. And of course, the vertex at 1, 2. So there's my point right there. And hey, since the y-intercept is here, we know that the y-intercept is going to go right there as well. We can go ahead and plot that point. Okay, next I'll reveal the work to find the table of values. So if you haven't done that yet, you might want to pause the video to see if you can come up with it on your own. Okay, go ahead, pause the video now. So we start with a normal table of values. We're moving to the right 1 unit. So we're going to add 1 to the x values. We're doing a vertical stretch and reflection. So that means we're going to multiply the y values by -2. That's how I'm coming up with these numbers. Finally, we move it up 2 units, which means adding 2 to the y values like this here. We do the order of transformations very similar to the way we would do the order of operations. If you think about it, we'd have to do what was on the inside of the parentheses first, that addition or subtraction. Then we would have to perform the multiplication. And finally, we would be able to add whatever was at the end of that. So that's the order we want to do these transformations in. Okay, we'll plot the points next. And finally, we get the curve that's over here on the graph when we plot the points that are in that table of values. You'll see that from my normal quadratic, it moved to the right one. It was reflected, it got narrower, and then it was shifted up 1 unit. This would leave us then with the range that y has to be less than or equal to positive 2, right? Because it's from here and down instead of up. One more example. Why don't you pause the video right now, and then I will reveal the answers to you momentarily. So go ahead, pause the video right now. See if you can do the whole thing on your own. Good luck, folks. Try it out now. Go ahead, pause the video. So here it is, folks, everything. You should get that a is equal to -1, right there. H is -1, right? Because remember, that would be x minus -1 to get it to be that plus that's in there, right? If we had that equation. So h is equal to -1. And then you have k is -3. Because a is -1, it would move down, or would open down. The parabola would open down. The y-intercept, when I plug in the work for 0, I get 0, -4. The axis of symmetry is at x equals the h value, -1. The vertex is h, k, -1, -3. Domains all real numbers. Once I plug in my table of values and I go left 1 unit, then I reflect over the x-axis, reflect over the x-axis by multiplying the y values by -1, and then move down 3 by subtracting 3 from the y values. I end up with this final table of values, which plots this quadratic here, which has a range of y is less than or equal to -3. Whew. That's a lot, folks. I hope you got it all. If not, be sure to ask lots of questions in class when I see you again. Otherwise, good luck.